Guys, my threat about the seating chart still stands. Okay, plate tectonic theory. What are these? These are hard-boiled eggs that have been cracked. Well, that's just like the Earth's lithosphere. Now, when we talk about plate tectonic theory, we've been talking about, what have we talked about? We talked about continental drift theory, proposed by Alfred Wegener. Everything was put together like a puzzle piece. The fossil evidence, the mountain evidence, the climate evidence. But there was no, what? What was the problem? Why was it rejected? Yeah, there was no way to get the continents to move. I mean, they were just static. And he's like, they moved, and they're looking at them. There's no engine. No, it didn't. Okay, then that's pre-World War II. Then we go post-World War II. We get Henry Hess, who says, hey, look at this. The seafloor is moving. It's dividing, and it's being subducted. The evidence is we got the earthquake patterns, and we've got the paleomagnetism, and we've got the seafloor ages. Right? So that's what we did last class. So, taking continental drift theory, which was rejected, we take seafloor spreading, which makes sense, and provides what? What does it provide to continental drift?
The method of how they move.
It provides the mechanism for movement, the engine or the method for movement of the continents. Aha! So they're like, wait a second, maybe this Wegener guy was right after all, but he was missing some stuff. So instead of having all these disjointed theories all over the place, let's come up with a unified, all-encompassing theory, law, whatever you want to call it, scientific thought on what actually is happening. So plate tectonic theory is putting it all together, and what it adds specifically is the motion. Okay? So we're specifically taking the motion driven by convection currents. And we're going to have to sit and talk about this for a second. We're going to have to talk about convection currents. But write it down. Now, the motion, they measured, this is measurable. The motion is 5 centimeters a year. Okay? So in 100 years, how many centimeters has it been? 500. What is 500? That's a half meter. Well, I mean, what is your desk? About a half meter long? Something like that? I mean, we're just taking rough averages. So the width of your desk is how much the Earth is moving in 100 years. It's not really all that much movement. However, it is constant movement over time, creating an incredible amount of force, and force over time equals cool stuff. Okay? So, since I gave you time to write this down, let's move on. Now, let's talk about this convection. This convection is very important. Okay? You've got to get the convection. So, let's talk about it. Convection. Convection currents in the mantle move plates. Now, the mantle. We've talked about how the mantle is kind of plasticky. It's like that deformed wax. It's under extreme amounts of pressure. So it's not moving very far, very fast, but we do believe that it does move. Now, convection is going to explain weather. It's going to explain oceans. Convection's everywhere. Why is it hotter upstairs in your house than it is downstairs? Why in the winter is it so cold you're downstairs and so hot upstairs? Because heat rises. Okay. If I take a piece of the mantle down here, well, what do we know about the deeper we go in the Earth? What does the heat do? What is it temperature-wise as we go deeper? What does it do? It gets seriously hotter, right? That's because of the pressure at the core of the Earth is much greater, which causes more heat. All right. Well, down here, we're going to write hot. Very hot. So does it make sense that the mantle next to the fire is going to be hotter than the mantle way away from the fire? Okay, so this is going to be cool. Now understand, hot, it's not cold or hot, it's much hotter here than it is here. Now, what happens to something when you heat it up? Okay, it could melt, it could do a complete change of state from solid to liquid. It might even go from liquid to gas, right? But what it does is it expands. Dietrich, that was great. When something gets heated, it expands in all directions. Right? Three-dimensionally it expands. If something expands but has the same mass, that means the volume is now increased but the mass is the same, what does that do to the density?
It makes it heavier. I mean,
Lighter, right? If something's expanded, it has more volume per density, that means it's less dense. Do you guys remember the salad jar illustration? Okay, what does the less dense stuff do? It floats. Okay, because it's now saying, wait, I need to get to where the less dense stuff is, and I need the heavier stuff to get down to where it is, so we can be happy mixed up, or happy separated salad jar. So the stuff here is getting hot, it's expanding, becomes less dense, so it moves up. Does that make sense? Okay, we're actually going to demo this later. Okay, it moves up. Well, as it continues to move up, if I take away the spot here, nature abhors a vacuum. So what happens? More mantle comes in to take its place. It continues to get hot because it's next to the fire. So that stuff moves up, and before you know it, you have a whole lot of mantle moving up. Right? Right? This happens in water, this happens in air, this happens in the mantle. So as this stuff is moving up, moving up, moving up, no, now it's getting away from the fire. Do you guys like campfires?
Yes.
Okay, except for Dietrich, everyone loves campfires. I love s'mores and marshmallows on a stick. It's just, life is good with s'mores. You gotta get rid of the chocolate and get Reese's peanut butter cups instead, and then your life is really content. Okay, now, the closer you get to the fire, the hotter it becomes. The further away you get from the hot fire, especially on a cold night, the colder you get, right? Same concept. As this stuff's getting colder and colder and colder, well, what happens to stuff when it's cold? Is it still expanding?
no, it's condensed.
No, it starts to condense, it starts to contract. So now everything starts to move in. What does that do to the volume? The volume then decreases, so now we have stuff that's more compact per mass. What does that do to the density? It gets more dense, so this is more dense as compared to less dense. Okay, this floats if it's less dense. How about if it's more dense? What does it do? Not only does it contract, it starts to sink. Okay. Now here's where convection, a lot of people understand, okay, less dense floats, more dense sinks, no big deal, what's the point? Well, if this is continually rising, and it starts to get cooler up here, so I'll even rewrite cool in a different color. Okay, so starting to get cool up here, and it wants to start sinking. Can it sink right back down? Why not? Because there's still stuff coming up. So it doesn't go right back down, it gets pushed sideways. So this, as it starts to cool off, it's getting pushed out of the way. Well, when it starts getting pushed out of the way, it bumps into this crazy thing called the lithosphere. Okay, lithosphere being our crust, and it pulls the crust with it. Because it's so, the friction, is tight, it's pulling the crust with it. Okay, so here at the spreading center, we call that ridge push. The ridge, there's so much pressure, the pressure is pushing the ridge out of the way. And down here, gravity's pulling the slab down, so this is slab pull. But this is all caused because the mantle is pulling it with convection. The friction's pulling it. And now, we have these sections where it's sinking, it's sinking, it's sinking. Well, the closer it gets to the core, it starts to get heated up. It starts to get heated up. Now that this stuff is being heated, can it go straight back up?
No.
Why not? Because you've got stuff coming down behind it. So now, do you see the convection cycle of heated rising, cooling, dropping, heated rising, cooling, dropping? Jack. Where? Here? 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 Well, what you've got here is the same thing. As it's coming down like this, it'll start to rise over here. Right? It'll rise over here. And then it gets cooler and moves this way. And then it comes back down. So what you see how you have a cell here, you have a cell here, you're going to have a cell here. You're going to have multiple convection cells in the planet. Does that make sense? I hope it does. If not, we'll do some demos. What?
8 demos. Like, since like it's half, put in the other half.
No, by demo I mean I'll actually get out some water and we'll put some food
Also
coloring
like
in.
the parts.
Okay? This is convection. Guys, if you get convection now, meteorology is going to be a breeze. Meteorology, the study of weather, is all about convection. Okay? Okay. So, I'm going to ask you a question. What is, I'll get to you in just a second. What is the driving mechanism that causes the plates to move? Convection. What does convection do to the plates? What was it? I'm sorry. What was that? Ridge pushes, slab pulls. Okay? The convection's actually like dragging the crust with it as the mantle's being forced in these cells.
You said ridge push.
Ridge push, slab pull. Okay.
What?
Okay. Christian.
So if it convention happened,
Hey guys, I'm trying to listen to Christian.
which way does the Earth will like?
Well, the Earth spins to the east, right? So the Earth is spinning, I believe, toward the east. This is all going on inside regardless of the spin. Okay? Like I can boil water, or I can, boiling water gives you convection, no, sorry. I can run on the surface of the Earth. Like today's my running day, so I have to go running today. So my goal is to run 4.5 miles. Okay, if I'm running and the Earth is spinning, does that prevent me from running? No, because you don't even notice the spin. So this is happening regardless of the spin.
But what I'm saying is like it's top like the ocean, which way does it move like 5 meters, like?
Okay. I think you're saying that you. Where is the movement of the crust? So from the center here, it's going to be moving in this direction and this direction at a rate of 5 centimeters a year. Okay? And if you get to the trench, it's being subducted at a rate of 5 centimeters a year.
That's how.
Alright, does that answer your question?
So like over here, like the continents are going closer or?
Throughout time, the ocean will get wider, and the ocean over here will get narrower. The mountains will get bigger. Right? For example, the Himalayas right now are continually getting taller and taller and taller. There's mountains in California that are getting taller and taller and taller, like very quickly. So, constant movement. This is why we have earthquakes. Okay. Does that answer your question? Oh yeah, still spreading, actively spreading. Okay. That's the hard part to understand about this whole thing. If you can get that, we're set, because the rest is easy. Okay, now slab pull, ridge push, and plumes. Slab pull, ridge push, plumes. Well, we've kind of talked about slab pull is where the plate is getting pulled into the earth and gravity is just pulling it like a guy with a rope down toward the center. The ridge push is where you have all that pressure being exerted in the middle, and that pushes the plate out. Well, slab pull, ridge push, and convection all work together to make the system go. There's a lot of conjecture on how this started, or why this started, or has it even always gone at the same rate. We don't know that. We're guessing because we see what it's doing today that it's always gone at this rate. We don't have any evidence to suggest otherwise. And we don't necessarily know why it started or how it started. This does not happen on other planets. Okay? This doesn't happen, I should say, on all the other planets. Like Venus, no plate tectonics. The Moon, no plate tectonics. Okay. Plumes, mantle plumes. A plume, you know, it used to be if you have a hat, we'll get a nice bowler hat. A plume would be this feather that people would put in their hat. Like it was a plume of feathers. I can't draw. But this was what, like, an original plume, P-L-U-M-E, not plum, plume. Well, a similar concept, instead of a plume of feathers, a plume in science is a outward jet of material. So if you have a plume of pollution in the groundwater, that's where all the pollution is being concentrated in one direction. We call that a plume. If you have a plume in the mantle, what you have is there's a certain spot where it's not a convection cell, where the mantle is just being pushed up. It's what we call a hot spot. Okay, that's a mantle plume. An upward movement of heated mantle material causes hot spots. Okay, a plume would be just this kind of a shape of a material going in one direction. Do you guys understand plume? Are you good? Okay. Abaj, you got that?
Yep.
Okay. Does anyone not get that? Do my counting to 10 thing. Okay. Okay, this is an outline. I'm going to be talking about stuff like divergent, convergent. Do you guys notice that there's not a lot of things to write down? Of course I'm going to go back. Okay. I'm not giving you a lot of, kind of on purpose, I'm not giving you guys a lot of stuff to write down. I want you to listen to what I'm saying and summarize what I'm saying in the notes. But this is the outline for the rest of my slides. And they're all pictures. I like pictures. Pictures are fun. Okay, so we're going to talk about divergent boundaries. There's continent divergent, and there's ocean to ocean divergent. Then you have, it's kind of a process. You know what, I mean, we would say that. It's the divergent process. Okay, then we're going to have convergent boundaries where they're coming together. Divergent, going apart. Convergent, coming together. If we're all converging on the same spot, we're all about to crash. Okay, convergent, now you can have the ocean and ocean converging. You can have the continent and the ocean converging, or you can have the continents and the continent converging, and it all does different stuff. These two are similar, but you get up with a different result. And finally, we'll talk about transform boundaries. So the big example of this is the San Andreas Fault is a transform boundary. They're moving, sliding past each other. But there's more transforms than just the San Andreas. Okay, so this is our outline. I'll give you guys a second to write that down. Okay, while you're writing it down, listen to what I'm saying here. Okay, plate tectonic theory takes everything from continental drift, the big ideas from continental drift, that the evidence is there that everything was put together at one point. It provides the mechanism. Seafloor spreading shows us that everything is moving. Plate tectonics gives us the mechanism. That mechanism means we're going to have boundaries between the plates that do certain stuff. Did you guys see where we are through the unit so far? Okay, and at every one of these boundaries you have earthquakes. Okay? So we start off with earthquakes, and we did continental drift, and we did seafloor spreading, and that all describes plate tectonics. We all together? You guys finish writing stuff down? Back one more? Back one more. No. We're going to keep going forward.
No.
Go online, watch the video. Okay. Divergent. Okay, the first thing we're going to talk about is this process of divergent boundaries. This is actually kind of cool. If you want to see this, now obviously the plates are moving at about 5 centimeters a year. You're not going to be able to sit down, get some popcorn, grab your Mountain Dew, and watch it happen. But what you can do is look at different areas of the Earth that are in different stages of the divergent plate boundary process. Okay? Stage 1, the Earth is starting to thin. Okay, the Earth is starting to thin because it has some convection starting up under it. Now, what do we notice? What is all of this crust? This is important. What is all this crust?
What do you mean?
It's continent crust, right? What are the two types of crust? Continent and oceanic. What is continent crust made of? Earth. What kind of earth? What kind of dirt? What kind of rocks? No, but you're on the right track. It's felsic. Okay, it's grit. Guys at that table, stop. This is felsic rock, mostly granite type of rocks. Okay? Now, after a while, this plume is coming up and breaking it all up. You see how it's cracking and fracturing? And it's starting to get, like, because the plume is going this way. And the more the plume goes this way, the pressure over time exerts such force that it literally rips the continent in half. Rips it apart. When that happens, you get a certain type of lava exposed. What did I say is always there with these mantle plumes? What kind of magma is this dark stuff? Starts with a B. Basalt. Very good, Jack. Basalt. So here we have this is coming up and breaking and breaking and breaking and breaking, and before you know it, it just gets ripped in half. Well, if it gets ripped in half and the continent's exposed, the magma is coming to the surface. The magma is almost always, as far as I know, it's always basaltic. So what kind of crust is being formed between the continents? Basalt. And basalt is part of, if it's not continent crust, it's ocean crust. Oh, wait a second. We're forming ocean crust between continent crust? That should trigger your mind to what might happen next. So what this forms is a rift valley. There are tons of examples of these, but the most beautiful examples you'll see is going from Africa into Palestine. So down here's Lake Tanganyika, okay, Lake Nyasa, Mount Kilimanjaro, Mount Kenya, Lake Victoria. The rift valleys go all through here. And you go into the Rift Valley and it looks just like this. You go over and oh look, there's a ridge, there's a valley, there's a ridge, and it's got lava flows in the middle. That's what Africa looks like all through here. Now eventually, we're going to realize that, wait a second, this stuff is thin compared to the continent. The oceanic crust is thinner compared to the continent. It's also more dense, so it's a little bit sunken down. These tend to be below sea level, right? Because all the continent's being ripped away. So they're going to be below sea level. It's oceanic crust. What's eventually going to fill up this valley? Water. Oh look, you're right. Water. So the third step in the process is you get these seas. A linear sea means a sea that's in a straight line. Linear meaning line. So here we have, it's been ripped apart, ripped apart, ripped apart. The oceanic crust is beginning to form. The divergent ridge is starting to develop. And now you have an ocean or a lake in the middle. Okay? Where on the map do we see that?
The Red Sea.
The Red Sea is a beautiful example of that linear sea formed by the earth literally being ripped in half. So eventually, the Middle East is going to go this way, Africa is going to go that way, and this is Somalia here, part of Ethiopia, down here to Tanzania, and other parts of Africa. These are going to get ripped off and go into the Indian Ocean. You're going to have an ocean forming between Africa and Africa. Okay? That will happen eventually. Maybe 50 million years. You don't have to worry about it. You don't have to worry about buying property. But it will happen. Okay? So here we have what looks like would be a great example of the Red Sea. Okay, Red Sea. Give the Red Sea enough time, and this rift in Africa will have a giant ocean in the middle of it. Okay? Where do we see an example of this kind of geology? Where you have a great mid-ocean ridge. The Atlantic. Now the Atlantic doesn't have as many trenches on the sides, but the Atlantic started off like this. Okay, let me give you a clue about the Atlantic, gentlemen and lady. You're a bad influence on something. Okay. This would be Virginia. Okay? Somewhere over here is going to be Africa. Okay, I might have my space, but that's basically the idea. Okay, in between Virginia and Africa, somewhere on this side you have a mountain range. This is the Appalachians. I'm sure I spelled that wrong. Okay, that's the Appalachians. When the Atlantic formed, this is what happened. We start getting this uplifting, the cracking, the fracturing, the magma, the basaltic magma coming up, filling in cracks, and before you know it, it rips apart. Well, has anyone heard of Culpeper? Does that sound like a local place?
Yeah.
Okay, we are living on the outside of what's called the Culpeper Basin. The Culpeper Basin is this. The Culpeper Basin is actually the Rift Valley. And as the Earth was starting to split, it had different rift valleys all over the place. And there's a bunch of different rift valleys. And eventually, the Culpeper Basin lost the battle to be the Atlantic Ocean. And the Atlantic Ocean formed somewhere out here, and it ripped apart. So now you have here, Virginia, Africa. Okay? Now you have this rift forming between Virginia and Africa. The Appalachians are getting divided. Some of the Appalachians go to northern Europe. Most of the Appalachians are in the east coast of the United States, North America. Okay? So this is going on. This happens to North America. This is when Pangea is splitting apart. Okay. Now you have the same thing. It's going to be Virginia, Africa. It's starting to split apart. Now way over here, ignore the trench, you have Virginia, you have Europe or Africa. Okay, it just continues to split, continues to split, continues to split, continues to split. And now you have a giant ocean in the middle because, you know, after 250 million years at 5 centimeters a year, you're going to get some space. Does that make sense? That's how the Atlantic forms. So we can see this in the Atlantic, the Red Sea. Where is this happening? Rocky Mountains. Where is this happening? Has anyone heard of Death Valley?
Yes.
Okay. You guys realize that Death Valley is actually below sea level? But there's a mountain range between Death Valley and the ocean. If there wasn't a mountain range between Death Valley and the ocean, it wouldn't be Death Valley, it would be Death Lake. Which they need to name it Death Lake, because that'd be really cool. Okay. Eventually, Death Valley will, look like this. I mean, it's a straight, long line. It's most of California, and it's below sea level. This will happen to Death Valley. Give it enough time. Okay. So you can see these active zones in certain parts of the United States. Is this happening on the East Coast? No, it's not. It's happening on the West Coast. So where do we expect to have the big earthquakes? The East Coast or the West Coast? West Coast. Does that make sense? Because that's where the action's happening. Okay. That is all divergent. So we're done with divergent. Whew! That took forever. Okay? Do you guys understand the divergent process? Yes. All right, come on. Okay. Now this is where I think it really gets fun. This is where I start having fun. Stay right there. Okay. Convergent is where all the action is. Okay? This mid-ocean ridge stuff is usually pretty peaceful, pretty calm. It just kind of slowly happens. You might get a volcano like Kilimanjaro, but usually you just have the ridges. It's boring. What do we have here? We've got volcanoes. Okay? We've got earthquakes. We've got Japan. Now, this is ocean to continent. Okay, we have oceanic crust moving in this direction. We have continent crust moving in this direction. The oceanic crust versus the continent crust is going to come together like this. Now, why is the oceanic crust lower?
Because it's more dense.
It's more dense. It's sinking heavier in the asthenosphere. Okay, they come to do battle. They crash together. Who's going to win? The continent's going to win every single time. The continent wins. So this crust gets pushed down. It's being subducted. It's being pushed under. Sub meaning under. Okay? And here's the trench to show that gap. It's being subducted. Well, when the crust gets subducted, it's already under the ocean. Do you think that rock is full of water? Yes, it's full of water. So this ocean water comes down here, and guess what? From what we understand, rock helps this stuff melt. So as it's coming further into the asthenosphere, it starts to melt. Now I'm not talking turning into mantle. Some of it does turn mantle-ish, but this stuff starts to melt. This particular crust melts faster than the mantle does. As it melts, you start to see these blobs of magma. Well, guess what? Magma is not solid rock, is it? It's liquid rock. It's lava underground. Wait. Is it liquid less dense than solid? Is it? Yes. So here you see these magma blobs are making their way up to the continental crust. Do you see how they get kind of stuck at the bottom of the continent crust? Turn it off, leave it off. Okay. See how it's stuck at the continent crust?
Yeah.
Okay, well that's because the continent crust is really resistant to being destroyed. So you get these slow little balloons. Now do you guys see these gray balloons?
Yeah.
This would be what kind of igneous rock? Intrusive or extrusive? Intrusive, right? Because it forms and cools in the earth. This would be something like a granite. An entire thing, a huge thing of granite. We're going to talk about the names of these later. Okay. And then eventually they break to the surface and you get volcanoes. When you have convergent ocean to continent, write this down, you get a continental volcanic arc. These always cause volcanoes. We call them continent volcanic arcs because they occurs on the continent. Does that make sense? Right? It's coming up through continental crust. This magma, by the time it gets up here, is a lot more felsic than it is mafic because it's had to go through all this felsic stuff. So, where would we see an example of this on the globe?
Japan.
Not Hawaii.
Japan.
Japan. No, actually not Japan.
Yeah.
Not Japan. Japan is ocean to ocean.
Yeah.
So it's same process, different crust. California? How about Northern California? I'll go with Northern California. Who's ever heard of Mount St. Helens? Anyone heard of St. Helens?
Yeah.
Anyone heard of Mount Rainier? Mount Hood?
Yes.
Shasta, the Three Sisters? All these mountains on the west coast, specifically in the Cascades. This is what they are. They're volcanic mountains. Okay? Let's take our gaze south to South America. What is the big mountain range in South America? You guys need to take geography. What's the big mountain range in South America? Starts with an A. The Andes Mountains. The Andes Mountains. A-N-D-E-S. The Andes Mountains next to Chile.
Oh, it's my country.
Okay. Yeah, Chile up into Peru. Right? That is all formed because of ocean to continent subduction. Okay? Now, there's that. Now let's talk about convergent ocean to ocean. Ocean to ocean. Well, this is Japan. Okay? So here we have oceanic crust, oceanic crust. Do you guys see how this is the exact same process? Except here you have oceanic crust to oceanic crust. Well, one of them is going to get subducted. Okay? Because oceanic crust already sits really deep. Now, which one do you think is going to get subducted? The older crust or the younger crust? Why do you think the older? Well, the less dense stuff is going to float higher. Because it's more dense. Because the further you get away from the source of the fire, the colder you get. So if the older crust simply means it's been on the ocean floor longer and it's had a chance to get colder, which means it's just a little bit more dense than the other ocean. So that's what gets pushed down. This is Japan. This is why Japan is such a volcanic hothouse of craziness. Okay, it's a pretty place from what my wife tells me, but yeah, they have crazy earthquakes and volcanoes and tsunamis. All right, what does ocean to ocean give you? What kind of an arc, volcanic arc, is this?
Island.
Yeah, it's a volcanic island arc. Oh look, it's an arc of volcanic islands. Okay, so you need to write down that convergent ocean to ocean gives you a what kind of island arc? A volcanic one. Volcanic one. Now, do you get lots of earthquakes or no earthquakes here? Tons of earthquakes. The 9.0 that just happened in Japan, this is why it happened. Okay? It's continent, ocean to continent, ocean to ocean, and finally with convergent we get continent to continent. Okay? Now continent to continent, this is kind of cool. I think this is neat because the continent's kind of a bully. If you think of these as battles between kids in the playground, you know, the kid who's bigger and mightier and stands taller is always going to win, king of the hill. Well, here we have two kids who are both mighty and tall and big and buff, and they smack into each other, and neither of them will lose, neither will go under, so they both have to rise to the top. So, continent refuses to be submerged. It just doesn't do it, and instead of getting submerged, it gets squished. So here you have two continent crusts, and instead of one going down, no, we will both win, and they smash into each other and go up. And what does this give you? Mountains. Okay, well, I mean, this always gives you mountains. It's either, are they volcanic mountains, or are they folded mountains? Okay, so here you see layers of the earth, and as they get pushed together, those layers just get crumpled and folded, and then those folds get shoved on top of each other, and those folds get shoved on top of each other, and this is what you get called a folded mountain belt. What would be a beautiful example of a folded mountain belt? The Himalayas. The Himalayas are a beautiful example of this, where India, the Indian subcontinent, has smashed into the Asian continent, and, well, you get really tall mountains. So this is fresh in the Himalayas. Where do we see an ancient continent-to-continent mountain belt? The Appalachians. Our Appalachians is this, except 250 million years later of wind, weather, rain, and bashing and washing away, they're no longer big anymore. Do you guys realize that we used to be sitting at the core of some pretty big mountains? Like 250 million years ago, we wouldn't be sitting on this little flat Virginia section. It would be huge. We were at the base of these mountains. You go to the Blue Ridge is the very bottom of this. Blue Ridge would be like way down here. But all that's been washed off the top. Does that make sense? Okay? This one's pretty simple. They crash into each other, nothing gets abducted, you get big folded mountains. There's not much to say about that. Okay, so here's an example of this. So here's the Indian subcontinent. Now obviously we don't know exactly what it's looked like forever, but we have a good idea of what it looks like, and it comes up, smash! And so you see here this entire mountain range. Up here would be Tibet, up here's China, and this is where India has smashed into it, and these are the Himalayas. This is where the crust is gotten all crumpled and folded and shoved in the air. Okay? So, India smashing into Tibet, okay? Thus you have what we have today. Okay? More pictures. Okay, last one. Oh my gosh, we're almost done. Woo! Much excitement. excited? Okay. Transform faults. Transform faults are simply crust moving next to each other without anyone trying to take over. These are the kids that get along in the schoolyard, not the bullies who someone has to win. These are the kids that like doing high fives as they pass each other. Why? Because you get earthquakes along here, but nothing's being driven under, nothing's being subducted, nothing's being thrown into the sky. Okay, this is simply shifting back and forth. We see this most often at divergent plate boundaries, where for some reason it diverges over here, and for some reason it diverges over here, and the cracks in between these fractures are just fractures. It's where it's splitting in different areas. Divergent plate boundaries are kind of boring, but they're not always perfectly in a straight line. They go a little bit here, a little bit there, a little bit here, a little bit there. It's no real rhyme or reason to it. We just kind of see what happens. Okay? That's a transform boundary. Where do we see this? Besides the mid-ocean ridges, what part of America do we see this? Not Mississippi. California. California. Okay? Oh, that's a quiz.
That is a quiz.
What is weaker? Hotter zone between the what? I can barely read that.
What is weaker? Hotter.
What is weaker? Hotter zone.
Please, probably y'all don't need to say it.
Okay, what's the answer? What's the weaker? The hotter zone beneath the lithosphere that allows for Earth's motion and outer show?
The crust.
Outer. I think it's C.
It's inner.
Oh, what is the weaker, hotter zone between the lithosphere? Oh, it's the asthenosphere. Yeah, it's the asthenosphere. What is the weaker, hotter zone between the lithosphere that allows for motion of Earth's rigid, the ridger atom showed is the crust. Okay, so it's the asthenosphere. How about 2? Alfred Wegener is best known for what hypothesis?
Continental drift.
Continental drift. I'm so proud of you guys. What's the name given by Wegener to the supercontinent he proposed existed before the current continent? Pangea. Very good.
No, it was Atlanta.
Support for Harry Hess's hypothesis of C4 spreading did not include B. Yeah, B. Granite rock in the ocean floor. Because the ocean floor is not made of granite, it's made of what?
Basalt.
Salt. Most of Earth's earthquake, volcanoes, mountains, buildings occur.
C.
This is actually really important. At plate boundaries. Do we live on a plate boundary? We're going to talk about why we had a big earthquake and we don't live on a plate boundary. Okay? But are we more likely to get an earthquake, or is, let's say, the Rockies more likely to get an earthquake? The Rockies. Okay. Complex mountain systems such as the Himalayas are a result of what?
Continental.
Yeah, the Himalayas, result of what? Yeah. Good job. Continent to continent. Which of the following mountain ranges was not the result of typical continent-to-continent convergence?
Andes.
Yeah, the Andes. The Alps, the Himalayas, and the Appalachians are all folded. Yeah. Okay? 3 more. What is the type of plate boundary where 2 plates move together, causing one of the slabs of the lithosphere to descend into the mantle, beginning and overriding plates?
C.
Is it B?
Alright, the only option here that works is a convergent boundary, right? Because what is it describing? One slab goes under another, so it's describing a convergent boundary. So we look at our options. How many of these are convergent?
2.
This one and that one.
D.
This one is continent to continent. Those are the 2 bullies that just kind of bump up into each other like sumo wrestlers. Okay? So it's got to be A. Got to be A. Most deep focus or really deep earthquakes occur near the deep earthquakes. Where the deep earthquakes go. Trenches. 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 Hey guys, look at this. Mid-ocean ridge, divergent. Rift Valley, divergent. Transform fault, divergent. That leaves only one that's different. Okay. One of the main objections to Wegener's hypothesis of continental drift was that he was unable to provide an acceptable
Mechanism for
mechanism for continental drift.